we go. All right, so let me just briefly go over the value chain that is carbon capture, utilization, and storage. So it's a combination of technologies where you have a point source or a source of carbon dioxide that you're capturing, such as in a power plant, an ethanol facility, a cement factory, and you are capturing that carbon dioxide and transporting it to a location where either it is used for some sort of material, building material or some other feedstock, or it is used in the storage, the geologic storage of carbon dioxide. So we're going to talk primarily about the end of that value chain this morning, the geologic storage. Carbon capture, let me just explain briefly the other parts of the value chain. Carbon capture is the separation of carbon dioxide from the entire emission stream. It's done one of two ways, either physically or chemically. If you physically separate carbon dioxide, you're using a membrane. If you are chemically separating carbon dioxide from an emission stream, you're using a solvent or a sorbent. And when I say separate, it's because when you see something coming out of a power plant like a smokestack, that's actually only about 20%, 17 to 20% carbon dioxide. The rest of it is water vapor and a few other gases. So in order to do carbon capture and storage, especially the storage end of things, you have to have pure carbon dioxide. So you want to separate out the carbon dioxide from everything else that's in that in the emissions. So there's two methods for capturing carbon dioxide. One captures larger volumes than the others. So at point sources, which I mentioned before, so a point source is a single source with a large concentration of carbon dioxide. So for example, I'm a source of carbon dioxide. I breathe in oxygen, I breathe out carbon dioxide, but I'm a really inefficient location to try and capture a significant volume of carbon dioxide. So somewhere like an ethanol plant where you have a pure emission stream of carbon dioxide that comes off of the fermentation of corn, then you can capture easily carbon dioxide that has a little bit of water in it. You remove that water, dehydrate it, and compress that gas to a liquid for storage. Direct air capture works by essentially extracting carbon dioxide from the atmosphere, essentially like a vacuum. And so to give you a sense of the scale of those things, direct air capture, there's a project in Iceland that is removing 4,000 tons of carbon dioxide a year using direct air capture equipment. In Decatur, the project that the Illinois State Geological Survey did in conjunction with ADM captured and stored 1,000 tons of carbon dioxide per day. And so you can see that there's a significant volume difference between those two. But the focus primarily, or I should say, that's the reason the focus is primarily on capture from point sources and industrial emissions, because they're large, easily diverted sources of carbon dioxide. Utilization is the use of carbon dioxide in concrete or other building materials. You can use it to create chemicals or grow algae for biofuels or animal feed. And this is a nice chart I like, or this figure that shows, you can use it in uptake for algae and bioproducts, mineralization to create wallboard and other minerals, and then catalytic pathways, chemicals, physical services. So all of those things are ways that we can use carbon dioxide, and we use quite a lot of carbon dioxide. Transportation is the moving of that carbon dioxide from the location where you captured it to where you're going to use it or store it. And that can be done by a truck, by a ship, by a pipeline. So it's literally moving compressed carbon dioxide from one location to another. Carbon storage, where we're going to spend the remainder of our time talking this morning, is the permanent storage of carbon dioxide deep underground in the appropriate or significant geologic formations, which I will refer to mostly as a reservoir. So the Illinois Basin has the potential to store tens of billions of tons of carbon dioxide. And when I talk about the Illinois Basin, it's a geologic feature that underlies most of Illinois, parts of Indiana, and Kentucky. And it's about 60,000 square miles in the aerial extent of it. And it's quite deep in the subsurface in Illinois. And it's essentially a hard rock basin that has filled over hundreds of millions of years with sediment, which then that sediment has turned into hard rock. If you think about a 7-layer salad, that's sort of what the Illinois Basin is. It's a hard casserole dish with different layers of different rock types. And what makes the Illinois Basin such a good location for the storage of carbon dioxide is that we don't have a lot of oil and gas in the rocks that are the most suitable for carbon storage. So there's very few well penetrations or other reason to disturb the rock at depth in Illinois. So let me talk a little bit about how storage actually happens. So the Earth stores water, saline fluids, oil, and natural gas in pore spaces in rocks. What I mean by that is if you look at this photo micrograph, which is essentially a microscopic view of a sandstone, you can see that there's a lot of round grains that touch each other in various places. The blue space that you see is pore space. And so that pore space below the water table is filled with something. At the depths that we look at doing carbon storage, the water that is in these pore spaces is about 6 or 7 times saltier than the ocean, and it's not usable for anything. But there is brine, I'll call it, in those pore spaces. So the way that carbon storage works is it's harnessing the Earth's natural trapping system to store carbon dioxide. And so we look at a couple of different properties, porosity and permeability. So porosity is the amount of those pore spaces, and permeability is how connected they are. So the analogy that I like to use is that Swiss cheese could be very porous, it has a lot of big holes in it, but it's not permeable because those holes are not connected, so nothing can really flow through Swiss cheese. On the other hand, Alpine lace, which is a different kind of Swiss cheese, has a lot of really little holes, some of which are connected, which gives it some permeability. You want those two properties because you want to be able to store the carbon dioxide in the rock in those pore spaces where you are injecting it. So what we look for when we are doing characterization of a location for the carbon storage is a package of rocks. We're looking for one rock that can hold carbon dioxide, so something like a sandstone where you have those grains of sand connected in 3-dimension, you have pore space that holds something already, and then something above it like a seal. So that's a different rock type, such as a shale, that is impermeable and doesn't have pore spaces, so nothing really can pass through it. So we're looking at 3 different properties. Injectivity, can you put carbon dioxide into a rock formation? Capacity, how much carbon dioxide can you store in that rock? And containment, can you be sure that the carbon dioxide that you have stored will stay deep in the subsurface? So this is a look at the Illinois Basin. The actual, the diagram here on the left shows the depth of the basin. So you can see that it is deepest in the southeastern part of Illinois and into Kentucky. And you can see a cross section underneath that shows that basin or that bowl-like shape. The rock formation in the Illinois Basin that we are primarily interested in is called the Mount Simon sandstone. And directly above the Mount Simon sandstone is a shale seal called the Eau Claire shale. At Decatur, the Mount Simon sandstone, for example, is about the top of the Mount Simon sandstone is 5,500 feet beneath the surface, and it is 1,500 feet thick. The Eau Claire shale sits directly on top of the Mount Simon sandstone, and it's about 450 feet thick at that location. So when you are storing carbon dioxide, what you've done is you've captured it, you've compressed it, you've removed any water, you've sent it, in the case of Decatur, you've sent it via a short 2-kilometer pipeline to the wellhead where it is at about 1,000 PSI. It's injected via a well into a very specific location in the Mount Simon sandstone, and then it is monitored extensively to ensure that you have a safe, effective, contained storage of that carbon dioxide. So let me talk a little bit about monitoring and the ways that we go about ensuring that the stored carbon dioxide is in fact staying where it has been stored. So there's a wide range of technologies that get used. Some of those happen along the well. So for example, you can have fiber optic cables along the well, which allow you to measure pressure and temperature in real time. We have ports that allow you to take fluid samples and pressure gauges, excuse me, which allow you to understand if there are any significant pressure changes in the subsurface. Excuse me. We also do a significant amount of characterization. And so one of the ways that monitoring works is that we collect data before, during, and after injection so that we understand the environment before any wells are drilled, before any carbon dioxide is stored, during the storage operations, which can last 20, 30 years, and then post-injection after the system is closed and according to EPA standards, and then that is also monitored in the post-injection years for periods somewhere usually around 50 years. So that's all done through deep wells, shallow monitoring wells, groundwater monitoring wells, and some of the same tools that we use to characterize are the tools that we continue to use for monitoring. So seismic is a good example. You maybe have seen one of these trucks. It's a truck that essentially it has a plate on it. That plate makes connection with the ground and it sends a sound wave, an energy wave, through the subsurface, and then the sound bounces off and is collected by geophone recorders at the surface, and that allows us to understand the rock type, whether or not you have any faults or fractures, and allows us also over time to take a 3-dimensional or 4-dimensional picture, sort of like a sonogram of the subsurface, which allows us to track where the carbon dioxide is. Monitoring is used to identify and mitigate risks, to verify storage, and to ensure human health and safety. And one of the best mechanisms that we have for ensuring that monitoring is happening and that safe storage is happening is through regulations that are administered by the United States Environmental Protection Agency through something called the Underground Injection Control Program. And the UIC program has a specific class of wells that regulates, governs basically how and whether or not you can store carbon dioxide through a well. So you can't just go out and do this. You have to actually submit a very rigorous permit application that gets reviewed by the EPA. It gets open for public comment. There's a federal process. And then once you have an approved permit, that gets then you're required, the operator is required to send quarterly data to the EPA to ensure that you are continuing to have safe injection operations. So this is a little bit more detail about the Underground Injection Control Program, and you can see here the type of well that gets built. They have the permit application processes, and it requires extensive site characterization, CO2 specific well injection construction. So for example, CO2 resistant cement, and you have to use chrome steel in the injection intervals. Comprehensive monitoring, and then you have to also demonstrate financial responsibility and how you're going to ensure that you will take responsibility for the stored CO2. This is just, I wanted to show you a little bit on the ground of this. These are the well operations that are happening at ADM's facility in Decatur. Some of you, I think, have maybe visited. It's possible to arrange visits. I would suggest getting in touch with the Illinois Corn Growers Association. But there's two sets of wells. There are two projects here. Collectively, these two projects have stored, excuse me, again, about 3.5 million tons of carbon dioxide, and CCS2 and CCS1 are the, excuse me, again, are the injection wells, and they're about a mile apart at Decatur. And what's happening is that CO2 is being captured at these little boxes at the bottom. Those are the compression dehydration facilities where they are capturing CO2 off of ethanol. It gets piped via a very short pipeline, either to VW or to CCS1 or CCS2. And that's about, they're storing about 3,000, or they can store, excuse me, up to about 3,000 tons per day. I also want to bring your attention to a report that was conducted at the request of the Illinois General Assembly by the Prairie Research Institute at the University of Illinois that houses the Illinois State Geological Survey, the Illinois Water Survey, and the remainder of the other surveys. And this is a comprehensive report that talks about all the things that I have mentioned here today, gives more detail and additional resources if anybody wants to do additional reading. So with that, I thank you very much. And Haley, I will turn it back to you.
Perfect. Thank you, Dr. Greenberg. So feel free to send us any questions you do have. I have a couple here. The first one is going to be, turn my camera back on here. It says, what is displaced by the CO2 when we inject it, and what happens to that substance?
So that's a great question. So there's actually very little displacement. The Mount Simon sandstone is under pressured, so it's not at full pressure. So because you have carbon dioxide is a compressible gas, when you collect it at the surface, it is a gas. And as you compress it, you take it through a 4-stage compression process, you are reducing the volume by about 270%. So what might be a balloon at the surface is a golf ball in the subsurface. So the volume that you're injecting and storing takes up less space. But what's really happening is that the carbon dioxide is a liquid, and it's going into the brine that's already stored or already present. So some of it dissolves into the brine and some of it remains discrete carbon dioxide that's physically trapped in the pore spaces. You will have some movement of the brine in the subsurface, and that's natural. I mean, that happens anyways, but that is one of the things that you are required to monitor from the federal EPA is you designate something called the area of review, which is the area where your carbon dioxide could exist plus a zone outside of that of a few miles, and then you're required to monitor that entire area to understand what's happening with the hydrologic flow and where carbon dioxide is in the subsurface.
Perfect. Another question we have here. I heard at Farm Progress Show that carbon sequestration projects are happening too fast, and we need to slow down and study what's actually going on before we move forward. Sallie, could you talk about the timeline for the ADM project and their partnership with our federal government? How long have you been studying this process?
That's a really nice question. Thank you. That allows me to take a little trip down memory lane. So whoever asked that, thanks so much. Excuse me. We have been working on, let me back up. So the federal government has been looking at the possibility and the viability of carbon capture and storage since about 1998. And the Illinois State Geological Survey and other organizations around the country participated in a program called the Regional Carbon Sequestration Partnership Program starting in 2003. So that the main research has been done for about 20 years. It was done in phases, very slow, very deliberate. The first phase was literally a characterization of what was the potential for carbon storage in the 7 different regions of which these partnerships existed. So the Illinois Basin, the Midwest Geological Sequestration Consortium, was the partnership that we led at the university and covered basically the area I showed on that map, Illinois, Indiana, and Kentucky. So we characterized what kind of rocks you could use, how much storage potential there was, and basically it was an assessment. The phase 2 of that project was small pilot projects to do small enhanced oil recovery projects, a small saline storage project, which is such as the project at ADM. And then the third phase was the Illinois Basin Decatur project for us. So that has been, that project started, our first meetings between the University of Illinois and ADM were in about 2005. And the project started in earnest in early 2008. So from 2008 to 2011, we did site characterization. We applied for a permit from the Illinois EPA and the federal EPA. We did characterization, both of the deep subsurface and the surface. And then from 2011 to 2014, we injected carbon dioxide at that first project, and we've been monitoring since 2014 when injection at that CCS1 well stopped. The second project at Decatur used the science and the information that we got from the first project to make it better. And that project started in around 2008, 2010, and was funded by the federal government through about 2017, 2018, and then has been funded by ADM since then. So it's been an extensive 20-year process to get to vet and to demonstrate that this technology works, that the CO2 is measurable in the subsurface, and that it's safe. And it's been a public-private partnership between the federal government, universities, industry like ADM, and it's been done around the United States. And we've spent decades, the last 2 decades, sharing the information and the knowledge gained from our understanding to be able to do this. Again, I keep using these words, but they're very important, safely and effectively.
Perfect. And feel free if you have a question to put it in the chat here. I got a couple more. One is, how do they know where the CO2 is located once injected? Will they know if the CO2 moves into an area where the storage operator does not have store rights?
So we use a combination of models that get created, excuse me, using the data collected during the injection process, and also you're required through federal regulations to monitor the area of review, and you would have some sort of mechanism, whether it's a stop light map or something, that if you had an indication that your CO2 was going where it's not anticipated to go, then you would mitigate your CO2 operations at the well or stop injection. The area of review includes the pressure, the elevated pressure from CO2 injection. So that essentially is a buffer between, where the CO2 is and where property might be that you don't have access to the pore space.
Okay, one other question here. Let's see. Could a leak occur from the storage area? And if so, what are the risks associated with that leak?
So a leak could happen. The most likely place that a leak would happen is not through the geology, but through the well or through other wells that are identified in the area of review. So when you do define that area of review, you have to determine if there are old wells or other penetrations that might be considered leakage pathways. And so what you would do is you're monitoring your wells, you're looking for temperature changes, pressure changes, which would give you an indication that if you had a leak, that you would stop injection, you would mitigate that at the well, which might mean you repair the well, it might mean you plug the well, but you would stop CO2 injection operations. If you were to have CO2 leak, we live in an environment where we're exposed to carbon dioxide all day, every day. So one of the major challenges actually with environmental monitoring is that you need to understand what is the signature of the carbon dioxide in systems where there is already natural carbon dioxide. So when you're characterizing or understanding your location, you're really looking at what carbon dioxide is there, what are the concentrations, how can we tell the difference, fingerprint wise between the CO2 that's being stored and the CO2 that's already present in the system. So additional CO2 in the natural system is not necessarily harmful. Where you have the potential for harm is if you had a rapid release of carbon dioxide, in which case you would, it's essentially like opening a fire hydrant or, a fire extinguisher, where it's an exothermic reaction, so you form ice crystals, so there might be safety hazards to somebody who is nearby. The other concern with carbon dioxide is that it is heavier than air. And so if you had an enclosed space and that filled with carbon dioxide, it could be in large quantities a suffocant. And so you would want to make sure, for example, that you know, in Illinois, as we all know, the wind blows a lot, especially out in the fields. And so we don't have a lot of super low-lying areas, but we have basements, and we have locations where you would want to make sure that you had some warning system associated with the potential for CO2. But CO2 in and of itself, in regular quantities, is not harmful.
Perfect. I think we have time for about one more question. This one says, these types of projects impact many different types of people that have different political beliefs. Do you think our government's interests or society's interests in capturing CO2 and reducing CO2 emissions will change from administration to administration?
That's a really great question. So, as we discussed previously on my walk down memory lane, I've been doing this for about 25, 30 years, and we've had several administration changes during that time period. What's been very interesting with carbon capture and storage is that it has remained a priority, regardless of whether we have a Republican administration or a Democratic administration. Sometimes the reason for that changes. So, for example, one administration might be concerned with national security, and another might be concerned with environmental climate change mitigation. So those are two pretty different things, and you know, we can agree or disagree on those. But what I've seen consistently with the federal government and the Department of Energy is that this remains an important and large part of our energy portfolio, and it is the major mechanism that's used in climate modeling to allow us to get to this sort of decarbonized industrial system that we hear about, net zero by 2030 and 2050. The only way that you get to those goals is by having carbon capture and storage as part of the energy portfolio. And Haley, if I could just say one last thing, I have always looked at our energy system as an integrated system. And I think about retirement and having a balanced portfolio. And it's important to have stocks and bonds and cash under the mattress and a bank account and land and all sorts of things in your portfolio. The same is true when we think about our national energy portfolio. We need oil and gas, we need nuclear, we need renewables, we need ethanol, we need biofuels, we need carbon capture and storage as part of that portfolio, which allow us to be flexible in a changing geopolitical world, but also in changing economic times. And so responsiveness, having that balanced portfolio allows us responsiveness to whatever the current conditions are that we face.
Perfect. And we did have one more question come in, so I'm going to go ahead and ask you that one too. Other stuff like natural gas is stored in geological structures. How does those substances behave compared with CO2?
I'm sorry, Haley, could you say that again?
Yeah, so it says other stuff like natural gas is stored in geological structures. How do those substances behave compared with CO2?
So they actually behave pretty similarly. When I mentioned the underground injection control program, anything that's injected into the subsurface is regulated by the federal EPA. And so carbon dioxide is not the only thing that we inject into the subsurface. There are 6 different classes of wells, one for hazardous or non-hazardous industrial fluids, wells related to oil and natural gas, saline solution, and then experimental wells, and also these CO2 wells. So the storage of natural gas is not regulated through the underground injection control program. It behaves somewhat similarly. The methane molecule is different than the CO2 molecule in the subsurface, but the storage idea is still the same. And one of the things that we at the university looked at early on was ensuring that if you had stored carbon dioxide and stored natural gas, how do you protect the resource that is that natural gas so that they're not really interacting with each other? So in Champaign County, where I live, we have natural gas storage. And so you want to make sure that you're storing that carbon dioxide deeper in the subsurface. I would just add to that, in a lot of places around the world, like the North Sea, where they're producing natural gas, you find natural gas and carbon dioxide co-located. And so carbon storage done by the Norwegians is primarily done because they wanted to develop a natural gas resource, and in the 90s, and the Norwegian government said you can't emit the carbon dioxide, so you're going to have to store it. So they separate those two and then store the carbon dioxide and use the natural gas.
Perfect. I think we did have one more question come in, kind of along those lines. Let me see where. So that says, I've heard of other CCS projects around the world that have failed. Why will this one be different here in Illinois? What's different about Illinois?
So I'll focus on why Illinois is a good place for carbon capture and storage. I can't really speak to failure because I think that is over 20 years of research. Not everything comes to the intended completion, but that does not necessarily imply failure as you're learning. But what makes Illinois exceptional for carbon capture and storage is we have the right package of rocks. We have a very thick sandstone, that Mount Simon sandstone, and the shale seal above it, the Eau Claire shale, and we have subsequent seals between the Eau Claire shale and the surface. So we have deep and well-suited rocks for carbon storage. We have very few well penetrations, so there's not been a lot of oil and gas operations or other reasons to create additional man-made penetrations into that. So it makes monitoring and storage safer and easier. And we have significant intellectual capacity and experience. There's a team at the Illinois State Geological Survey that's been working on this for 25 years, and we understand the geology of the Illinois Basin because the Illinois, Indiana, and Kentucky Geological Surveys have been working together for 150 years to understand the rocks in the basin. So we have very viable sources of carbon dioxide from ethanol production, and which is easily captured, easily dehydrated and compressed, and a very, very viable source of carbon dioxide, which is 100% pure CO2. And that's possible because of the agriculture that we have available to us and the work that all of you do of growing corn and providing that to companies like ADM to make ethanol and other products. And so we have the full package of available resource, the natural resource of the subsurface and our agriculture system that allows us to be a full, complete system in Illinois.
So I think that does wrap up all the questions that we have been given. If anyone later does have any questions, feel free to send us an email and we can get those to Sallie and get all of your questions answered. But thank you so much for attending the webinar, and thank you so much to Dr. Greenberg for sharing with all of us your expertise too.
Thank you, Haley. Everybody have a nice day.